Let us continue with our discussion on elastic pressure transducers. In our previous class, we talked about Bourdon gauges. Today, let us talk about the next elastic pressure transducer, let us say bellows pressure gauge. A bellows element is a one-piece expansible, collapsible and axially flexible member. Bellows are essentially thin-walled cylindrical cells with deep convolutions and are sealed at one end. The sealed end will undergo axial displacement when pressure is applied at the open end. This is a schematic of bellows element. It is essentially a thin-walled cylindrical cell with deep convolutions. It is sealed at one end, and the other end we can apply the process pressure. If I apply pressure here, the sealed end will undergo axial displacement, which can be read by the deflection of the pointer against this scale. So, it is essentially a collapsible member sealed at one end. It has deep convolutions made of thin metallic shells. When I apply pressure at the free end, the sealed end undergoes axial displacement, and that displacement is a measure of the pressure being applied. This is a better representation of the bellows element. You have the bellows with deep convolutions. It is spring loaded inside, so that the deflection can be controlled, and this deflection is read by this pointer and scale mechanism. So, you have a connecting link and you have a sector and guinean assembly, sector and pinion assembly, which helps this deflection to be read by the movement of the pointer against this scale. Bellows are made of materials with good elastic property such as brass, phosphor bronze, beryllium copper, etc. They are all alloys. Stainless steel is also sometimes used. Although it is not highly elastic, but because of its good anti-corrosive property, we sometimes use stainless steel. Carbon steel is not a good choice because it gets easily corroded and it is also difficult to machine. Bellows elements are used for measuring lower pressure. It is more sensitive than Bourdon tubes. The nominal range over which a bellows element can be used is about 5 inch of water to about 100 psi. Bellows pressure gauge can be used to measure gauge pressure, differential pressure as well as absolute pressure. Let us look at this arrangement. We have two bellows connected with each other, and we have attached a pointer to the link that connects these two bellows. Now, when these two bellows are connected to a differential pressure source, the combined movement of the movement of the pointer against this scale will be a result of the combined motion of these two bellows. So, in that case the movement of this pointer against the scale will be a measure of the difference between P1 and P2 or the differential pressure. If one of these pressures is atmospheric pressure, it is measuring gauge pressure. If I seal one of these bellows and it is evacuated, so there is zero pressure inside, in that case the bellows element will measure absolute pressure. So, to measure absolute pressure with help of a bellows, what we will do is one of these bellows will be evacuated completely and sealed, so that it has zero absolute pressure. So, in that case the pressure that is being applied here will have a reference against zero absolute pressure. In other words, we can measure absolute pressure. Next, let us talk about another elastic pressure transducer, the diaphragm pressure gauge. Diaphragm pressure gauges are based on the deflection of a flexible membrane that separates regions of different pressure. So, diaphragms are nothing but a flexible membrane. It can be made of metal, it can be made of non-metal as well. The deformation of a thin diaphragm is dependent on the difference in pressure between its two faces. So, if I have a thin flexible membrane, let us call it a diaphragm, and two different pressures are being applied on two faces, then the deformation or the deflection of the thin diaphragm will be a measure of these two pressures that are being applied on its two faces. The amount of deflection is repeatable for known pressure, so pressure can be determined by using suitable calibration. Both metallic diaphragms and non-metallic diaphragms are used for pressure measurement. Let us now talk about the diaphragm pressure gauge in little more detail. A metallic diaphragm pressure gauge uses a thin flexible diaphragm of materials like brass, bronze, monel, nickel spancy, etc. All these materials have very good elastic property. The force of the pressure against the effective area of the diaphragm causes a deflection of the diaphragm. The motion of diaphragm is a measure of pressure, and the motion of diaphragm operates an indicating or recording type instrument. This is a schematic of a diaphragm element. So, when a pressure is applied here, there is a translational movement of this diaphragm element. This movement of the diaphragm can be used to move a pointer and scale mechanism. So, the deflection can be read, and that will be taken as a direct measure of the pressure being applied. Diaphragm can also be made of non-metallic elements such as rubber, plastic, leather, etc. Diaphragm gauges are typically spring loaded, so that the range and sensitivity can be varied. For non-metallic diaphragms, they are usually spring loaded because non-metals do not have good elastic property like metals such as brass, bronze, monel, nickel, spancy, etc. Diaphragm elements can also be used for measurement of differential pressure as well as absolute pressure. An approximate relation between the pressure differential and the normalized deflection of the diaphragm at the center is given by this equation. So, this equation relates the pressure differential to the normalized deflection of the diaphragm at the center. Let us consider this schematic. This is the diaphragm when there was no deflection. Now, P1 and P2 acts, P1 and P2 are two different pressures, they act on this diaphragm and there is this deflection at the center. This deflection can be made normalized by dividing this deflection by the thickness of the diaphragm. So, this equation relates that normalized deflection to pressure differential P2 minus P1. So, the deflection of the diaphragm at the center depends on elastic modulus of the material of the diaphragm, thickness of the diaphragm, diameter of the diaphragm and the Poisson's ratio. In this equation, E is elastic modulus, T is thickness of diaphragm, R is normalized deflection, which is deflection at the center divided by thickness of the diaphragm, and D is the diameter of the diaphragm and mu is the Poisson's ratio of the diaphragm material. This equation is highly nonlinear. For a linear relationship, the requirement is this quantity 0.488 r cube should be much less than r, so that this can be neglected. In that case, we will get a linear relationship between normalized deflection of the diaphragm at center and pressure differential. This schematic shows how we can measure differential pressure with help of a diaphragm element. We have a diaphragm here. So, this diaphragm divides this into two chambers. In one chamber, we apply pressure P1, the other chamber we apply pressure P2. So, the movement or the deflection of this diaphragm will be dependent on P2 minus P1. So, this deflection can be read again by using a pointer and scale. We have to attach a pointer and scale with this diaphragm through appropriate mechanism, and the deflection of this diaphragm will be a measure of the pressure differential P2 minus P1. Again, if I evacuate one chamber and seal it, we can measure absolute pressure. So, one chamber is evacuated completely and sealed. So, it has 0 absolute pressure. In that case, the deflection of this diaphragm will measure absolute pressure. Sometimes we form a capsule by joining two diaphragms at the periphery. So, we take two metallic diaphragm and join them to form a capsule. The sensitivity of the pressure gauge can be increased by cascading several capsules. So, we can form several such capsules and cascade them. So, we will have an assembly of capsules. When a pressure is applied to the capsule assembly by an inlet pipe passing through the center of all the capsules, the deflection of the gauge will be the sum of the individual capsules. One such capsule is shown here. Imagine several such capsules are stacked and this inlet pipe passes through the center of all the capsules. Then the pressure applied through the inlet pipe will cause a very large deflection of the pressure gauge. So, we can increase the sensitivity of the pressure gauge substantially. This equation, an empirical relation, tells us how much deflection will there be if we have n capsules in an assembly. This is an empirical relation which gives an estimate of the deflection of the pressure gauge, and it shows that it depends on number of capsules, the pressure differential, the diameter and the thickness. K is a constant for the gauge. For most practical cases, these exponents m and n are chosen as m equal to 4 and n equal to minus 1.5. So, if we increase the number of capsules, there will be more deflection. After talking about pressure measuring instruments that are used for measurement of moderate pressure, let us now talk about how we can measure very high pressure. We are talking about pressures as high as 7000 bar. We can use an instrument called wear coil in bellows. Measurement of pressures above 7000 bar is normally carried out electrically by monitoring the change of resistance of wires of special materials. So, to measure very high pressure, we monitor the change of resistance of wires of special materials with pressure. Materials having resistance pressure characteristics that are suitably linear and sensitive include manganene and gold chromium alloys. So, we use manganene or gold chromium alloys because they have suitable resistance pressure characteristics. So, a coil of manganene or gold chromium alloys is enclosed in a sealed kerosene filled flexible bellows. The unknown pressure is applied to one end of the bellows, which transmits the pressure to the coil. The magnitude of the applied pressure is then determined by measuring the coil resistance. Pressures up to 30,000 bar can be measured by devices like the manganene wear pressure sensor with a typical inaccuracy of plus minus 0.5%. So, to measure very high pressure, we take wires with good resistance pressure characteristics. Such materials are manganene and gold chromium alloys. A coil of such wire is enclosed in a sealed kerosene filled flexible bellows. The unknown pressure is applied to one end of the bellows, and this pressure will be transmitted to the coil. So, the coil's resistance will change according to the magnitude of the pressure. Therefore, the magnitude of the applied pressure can be determined by measuring the coil resistance. We can measure pressures as high as 30,000 bar by devices like the manganene wear pressure sensor. We have talked about transducers in detail before. We can very easily convert the elastic pressure transducers to a transducer that gives us electrical signal. Think of a Bourdon tube as shown here. Here, the Bourdon tube is converted to a potentiometer type transducer. So, instead of reading the position of this pointer against the scale, instead of reading the position of the pointer against a scale, this will the pressure can be read from the electrical signal, that is the output, from this transducer. The same way, a bellows element can be easily converted to a potentiometer type transducer with help of this Wheatstone bridge circuit. As the process pressure changes, the position of this pointer or the connecting rod changes. So, the output of the Wheatstone bridge circuit changes. So, that electrical output will be taken as a measure of this process pressure. So, the basic function or the way these two different pressure measuring elements are converted to a potentiometer type transducer is same. We can also use a linear variable differential transformer or LVDT to convert these to a transducer that gives us electrical signal. Because we have seen in our previous lectures that LVDT is a distance measuring transducer. So, the deflection of this pointer or this pointer or connecting rod can also be converted to an electrical signal by using LVDT. Let us now briefly talk about how we measure pressure of corrosive fluid. When you want to measure the pressure of a corrosive fluid, it is necessary to protect the pressure gauge from the effect of the corrosive fluid whose pressure is being measured. So, you should avoid direct contact of pressure gauge and the corrosive fluid. We can make use of a diaphragm seal or liquid seal known as seal pot to avoid direct contact between the pressure gauge and the corrosive fluid. This can be done as follows. This is the pressure gauge. And let us say this is the corrosive fluid. We use a diaphragm element here. It may be a thin metallic diaphragm, or it may be made of say neoprene, etc. This entire part is filled with a sealing liquid. So, this is completely filled with a sealing liquid. It may be glycerin, or some oil, and this is the corrosive fluid. So, now I want to measure the pressure of this corrosive fluid. So, we have a diaphragm here which receives the pressure, it deflects, transmits this pressure to this pressure gauge through this sealing liquid. So, the diaphragm element does not allow this corrosive fluid to come in direct contact with the pressure gauge, but transmits the pressure to the pressure gauge through this sealing liquid. So, that way we can protect our pressure gauge. We can also make use of a seal pot or sealing liquid. So, you have a sealing liquid, you have a seal pot, this is the sealing liquid. This is the pressure gauge and this is the corrosive fluid. So, again the corrosive fluid is not being allowed to come in direct contact with the pressure gauge. So, either with help of a diaphragm element or a liquid seal, we can protect our pressure gauge when we use it for measurement of pressure of corrosive fluid. Let us now talk about high vacuum measurement or measurement of very low pressure. We have several instruments for measurement of very low pressures. So, we are talking about pressures starting from say 1 torr to up to 10 to the power 7 or 10 to the power minus 10 torr. The instruments commonly used for measurement of high vacuum or extremely low pressures are McLeod gauge, which is essentially a modified manometer, ionization gauge, thermocouple gauge, Pirani gauge. Working principle of thermocouple gauge or Pirani gauge are related. Together they can be clubbed as thermal conductivity gauge and also Knudsen gauge. This is not much used these days, but these instruments are widely used for measurement of very low pressure. So, let us start our discussion with McLeod gauge. So, McLeod gauge is essentially a modified manometer. Let us draw the picture first. This is a movable reservoir. So, this is mercury. This is capillary, as indicated by C. This is bulb called B. Here we have an opening, that is called O, and this is the flexible tube which connects this to the movable reservoir. So, this is a McLeod gauge, which is nothing but a modified manometer. We have a scale attached here. So, we have scale here. This is 0, 1, 2 and so on and so forth. So, this is the 0 reading. This is the 0 of the scale. So, let us say this is all filled with the mercury. This is okay. So, this is the construction of a McLeod gauge, which consists of a capillary, a bulb, and this is connected to a movable reservoir. We can bring it up or down. The way it works is as follows. The movable reservoir is lowered until the mercury column drops below the opening O. As we move this reservoir up or down, the level of the mercury in this capillary bulb will go up or come down. So, the first step to pressure measurement is lower the movable reservoir until the mercury column drops below the opening O. So, when it drops below opening O, the bulb B, the capillary C, are connected to the same pressure source as this. This one is connected to the vacuum whose pressure I am going to measure. So, this is to vacuum, let us call P. So, this is connected to the vacuum or low pressure source whose pressure I am going to measure. So, first I lowered the movable reservoir until the mercury column drops below point O. So, when it goes below point O, this entire thing is connected to the same low pressure source or same vacuum. Now, so that was first step. In the second step, the reservoir is raised until the mercury fills the bulb and rises in the capillary to a point where the level in the reference capillary is located at 0 point. The second step is the movable reservoir is now raised, and as we raise the movable reservoir, the mercury level, the mercury also goes up here, and we stop when the mercury column in this reference capillary, call this reference capillary, we stop when the mercury level touches the 0 of the scale in this reference capillary. Imagine under such situation, this measurement is y. We will now see that from this y, which is the length of the capillary occupied by the gas, the same gas whose pressure I am going to measure, will be used to compute the pressure. So, the measurement has two major steps. In the first stage, the movable okay, this is connected to vacuum or low pressure source. The movable reservoir is lowered such that the mercury level falls below point O. In that case, the entire capillary bulb, the reference capillary etcetera is connected to the same pressure source. In the second stage, I raise the movable reservoir. So, the mercury level stops going up. When it crosses the point O, see that this part is now disconnected from the low pressure source. So, in fact, the gas inside is being compressed. So, I continue to raise the movable reservoir until the mercury layer in this capillary, reference capillary, touches the 0 of the scale. Under such situation, let us consider the length of the gas in the capillary is y. So, this length is y. Now, let us see how we can calculate the pressure P from the measurement of y. Let us consider the volume of capillary per unit length is A. So, volume of the gas in the capillary if we call it Vc should be equal to A into Y, because A is the volume of the capillary per unit length. My length is Y. So, the volume of the gas in the capillary Vc is A times Y. Let us consider the volume of the capillary plus volume of the bulb and the volume of the tube down to point O, opening O, that means this entire part is Vb. So, let us denote the volume of the capillary, volume of the bulb and volume of the tube up to point O is Vb. So, when we started raising the reservoir at second stage and when we reached point O and got this part just got disconnected, I have Vb as the volume of the gas and I have now A times Y as volume of gas when the mercury rests at 0 in the reference capillary. So, initially I had a gas of this volume with pressure P. Now, I have a gas with this volume with some other pressure. If we consider isothermal compression of the gas in the capillary, I can write Pc Vc equal to P into Vb, where Pc is the pressure of the gas in the capillary now after compression, or we can write Pc equal to P, which is the unknown pressure, Vb by Vc. Now, the pressure indicated by the capillary, we can write as Pc minus P equal to Y. Now, if I use this relationship, and this relationship. If we combine these three equations, we can write P, the unknown pressure P, equal to A y square by V b minus A y, which can also be written as y V c V b minus A y. Since this volume is much less than this volume of this capillary plus bulb and plus volume of the tube up to point O, that means since A y is much less than V b, we can write from this P equal to A y square by V b, because we can safely neglect A y as this is much less than V b. So, finally, the pressure P is related to this measurement y. For a given McLeod gauge, A and V b is fixed. So, P depends only on y. So, for measurement, from the measurement of this y alone, which represents the length of the capillary or the length of the gas in the capillary, I can measure the unknown pressure or unknown vacuum P. We need to remember one thing here, that the McLeod gauge is sensitive to condensed vapors that may be present in the sample, because they can condense upon compression, and then the relationship PCVC equal to PVV may not be valid, because the working of the McLeod gauge depends on this relationship. We should ensure that this holds true. We can measure pressures up to 10 to the power minus 4 torr using McLeod gauge. One important observation about the McLeod gauge, you should note that the pressure is being measured from this dimension alone for a given McLeod gauge. So, in the range up to 10 to the power minus 4 torr, the McLeod gauge is often used as a primary standard. We still have some other pressure measuring instruments to discuss, which are used for high vacuum, namely ionization gauge and thermal conductivity gauges such as thermocouple gauge and Pirani gauge, and we will discuss this in our next class.